Okay, so today we're going to be doing some things with radical notation for what we call nth roots. First off, let's talk about radical notation and nth roots as defined in this box here. What this says is when x is non-negative and n is an integer greater than or equal to 2, then this holds true. Now we're familiar with seeing things written as roots, like cubed root, third roots, fourth roots. What this is doing is it's saying that if I have something that's written like this, the fourth root of x, I could also write that as x to the 1/4 power. Okay, so whatever the root is, that goes in the denominator here. And for the time being, the numerator will be 1. Sometimes that could change, and we'll see what that would change to in the future, or when that would change. But just know, like if we see the third root of x, that could also be written as x to the 1/3 power. Okay, now let's move on to something slightly different here. Suppose, this is a review here, suppose a set has n values. If you add the values and divide by n, you have found the arithmetic mean, or the average. Okay, that's nothing new. So basically, to find the average, we know we add up all the numbers and divide by how many there are. If instead of adding, you multiply the numbers in the set, and then instead of dividing, you take the nth root of the product of the items in the list, you find what's called the geometric mean. Here's what this means. To find the geometric mean, just like we said, we multiply all the numbers together. And let's say if there's 7 numbers that we're multiplying together, we would take the 7th root of the product. Or if there's 9 numbers that we multiply together, we would take the 9th root of the product instead of dividing by 9 or instead of dividing by 7. Now, why would we need another mean here? Well, an average works good if all the numbers are around the same value. But let's say if you have a number that's really, really high or a number that's really, really small that's going to throw off the average isn't going to give you an accurate description of where all the other numbers are at. So the geometric mean can be used when numbers are quite dispersed, to keep one very large number from disproportionately affecting the measure of center. Like, let's look at this example. Here it says, in a water quality survey, 8 samples give the following levels of E. coli bacteria. And this is the values down here in the bottom row are in counts per 100 milliliters. So in sample 1, there was 2 for every 100 milliliters. In sample 2, there was 54. In sample 3, 145, and so on. Well, as you look at that, this 1,152 there's a big difference between 2 and 1,152. Most of these, the 2 and the 54 and the 38 maybe are kind of small, but most of these are around the same value between 0 and 600. But 1,152 is almost double the next largest number. So that 1,152 is going to throw off the average. In fact, if we were to find the average here, if we were to add up all these numbers and divide them by 8, the arithmetic mean would end up being 302.4. Okay, we're not asked to find that, but I give you that just so we can compare that to what the geometric mean is. So to find the geometric mean, what I would end up doing is I'm going to multiply all these numbers together. This is something obviously you're going to do on your calculator. So we would multiply all those numbers together and we'll get an answer, but that's not our geometric mean. We still have to take the root. So there's 8 numbers I'm going to multiply together here, so I'm going to take the 8th root of that. Remember what we talked about at the beginning? Saying x to the 1/3 power is the same as the cubed root. So me writing this to the 1/8 power is the same as saying we're taking the 8th root. And when you do that on your calculator, you end up getting 102.6, or about 103 parts per million, per 100 milliliters. That's a big difference from the arithmetic mean. This gives you a better measure of center than this does for this particular problem, because the arithmetic mean doesn't take into consideration the fact that this 1,152 is going to throw off your data, where the geometric mean adjusts for that. Okay, so why don't you guys find the geometric mean of these populations? Again, you can see you have a large spread of data here going from 47 all the way to 45,312. So the arithmetic mean, I'll just tell you, is going to be for this particular problem would be 9,894.45. So why don't you guys take a minute now and find the geometric mean for this data, pause the video, and then hit play when you have your answer. Okay, so you should have multiplied all these numbers together and then taken the 8th root of them. Just so happens to be that there's 8 numbers in both these examples. You're not always going to take the 8th root. Again, whatever number of numbers you're multiplying together, that tells you what root you're going to do. So we take the 8th root, and you end up getting the geometric mean you find to be 1,656 approximately people per square mile. Again, a big difference from the arithmetic mean. Okay, so looking at this, remember I said at the beginning, when we saw problems like this, the 4th root of x, I said when we write that with an exponent, we would say it's x to the 1/4 power. Remember I said the root out here goes in the denominator. The numerator oftentimes will be a 1, but sometimes it can be another number as well. That's what this box addresses. What this box is saying is that if I have the nth root of x, and that x has some exponent, that exponent goes in the numerator, the root goes in the denominator. So in other words, the n represents the root, the m represents the power. Okay. You're going to see some problems like this in your homework assignment, where it talks about, here we have the square root of the square root of the square root of 6. We need to rewrite that using rational exponents. Now I want to talk about something here. When we see symbols like this, this is what we call radical form. Rational exponents is, like in this box, the second part of this box that we were just dealing with, means that we're going to be dealing with an exponent. So they want us to rewrite this using rational exponents. And so what we're going to do here is we're going to look at this as being 6 to the 1/2 power represents just this first root. 6 to the 1/2 power raised to the 1/2 power represents these first two roots. 6 to the 1/2 power to the 1/2 power to the 1/2 power represents all three of those roots. Now remember from when we talked about exponents, when we have all of these exponents, we would multiply these together. So 2 times 2 times 2 would give me 8. So this would be the 8th root of 6, or 6 to the 1/8 power. And so is this expression an nth root of 6? We would say yes, it's an 8th root of 6. This would be your answer. Okay, why don't you guys work on this next one and figure out what this would end up being using rational exponents. So pause the video and then hit play when you're ready to go. Okay, what you should have gotten here, to write it out the long way, you'd say it's 10 to the 1/2 power. Again, that represents just that first root. The 1/2 power represents now those first two roots. Do it again. And again, represent all four of the roots. And I multiply those together. 2 times 2 is 4, times 2 is 8, times 2 is 16. So this would be the 16th root of 10 would be the answer. Okay, so hopefully you got all that. Let me know if you have any questions. And good luck on your homework assignment.